Hi, everybody. Today, we're going to kind of make a little bit of a change. It might seem that way anyway. We spent some time dealing with some solving quadratic equations and getting better at that. We then jumped in and we started dealing with some system stuff. Well, now I want to kind of nail some stuff down. So what we're going to do is move away from the whole equation aspect, and we're going to jump into a function. And so you'll see the title for today that we're going to actually specifically deal with finding the vertex of a quadratic function. Now, what you see on the screen is our two forms of our quadratic function. Now, there is a third form that's generally dealt with, and so if you have some experience in the past with something that looks like this, that would be our factored form for a quadratic function. I'm not saying it's like an inferior form, by no means. It's just that our focus today is going to be dealing with standard and vertex. So we're going to kind of nail down those two parts. Okay, a couple things that I just want to nail down as we go. And I'm hoping again that this is all background. It should be for all of us. However, I do think that there might be a little bit of review that's going to be needed. Okay, let's focus in on the red, our standard form. When we read that standard form, I'm hoping that we understand that one of the benefits of that standard form is that we know that that c value would represent the y-intercept of our function. So when our function is written in standard form, so everything's expanded, collected, and in this case written in standard form, which means decreasing order, so my x squared first, my single x, then my constant, we should be good to recognize that that constant is going to represent the y-intercept. Now, you can tell that because you know you could always sub in an x equals 0, and you see that wipes everything out, and we're left with c. Okay, now I want you to turn and focus on your vertex form. So we're looking at the green. One of the benefits of your vertex form is that, based on the name, we can read the vertex. That parabola, if it's written in that form, would have a vertex at age k. Again, all review. The one part that I want you to notice that is the same between both functions is that a value. And if we recall, that a value from our transformations talks about the shape. We would address that as like a vertical stretch by a factor of a. So that's going to determine for us how steep or how flat that parabola is. There's the benefit of both forms of those functions. One, you can dictate the shape and you can tell the y-intercept. In a lot of cases, that might be like a starting value. In your vertex form, you can see the most important point, the vertex, the change of direction, as well as your shape. What we're going to spend our time doing today is talking about the benefit of both forms and changing between forms. Specifically looking at the title today, we're going to go on the hunt to find the vertex. Okay, let's jump in. So what I want to do is I just want to take a moment to let's transition between forms. So let's convert. As we get going, this is going to get pretty ugly at times. And I want to make sure that we don't get lost in the ugliness. So I'm going to kind of warn you a little bit. This is going to look bad. At times you're going to go, I don't even know what we're doing or why we're doing. Just hang on a little bit as we go. So I'm going to take a look at that instruction almost in blue, a little heading. And we're going to convert our vertex form into standard form. So for us to do that, that means that I would have to go through and expand all my brackets and collect like terms. If I go through that process, I can expand my brackets, so square the first, multiply those together, square it, square the last. And now as I go through, I could multiply in my a. Common form for most terms is going to say, write your variables in alphabetical order. And we get down to there. Notice I have nothing that I can collect like terms with. Okay, I know that looks really weird, but that is my standard form for a generic vertex form. I'm going to just highlight, there's my x squared term, there's my single x term, there is my constant. So if I wanted to look at that, I can tell that that is my y-intercept. A times my h squared plus k. Now, I started off saying, you're going to look at this and go like, but why are we even bothering? And I'm going to argue to you, I 100% agree. That us taking our vertex form and converting it into standard form doesn't really help us that much. Like, it does allow me to say, oh, well, if that's my y-intercept, then up here, if I ever wanted to know what the y-intercept of my vertex form was, then what I need to do is I need to take my a value, multiply it by my h squared value, and then add on k. Okay, can I just get you to see that if I gave you that original and I asked you to find the y-intercept, then all we have to do is sub in x equals 0. And when I sub in x equals 0, do you notice we come to the same thing? It's your a. I don't care that it's a negative h versus a positive h, because I'm going to square it and it's going to turn it positive anyway. And add on your k. So I would argue to you, does knowing that your y-intercept is a h squared plus k and trying to spend time remembering that really any benefit to you? Probably not. Because if you ever needed to find the y-intercept, you could just do the green, and the green is pretty quick. So for us to take our vertex form and try to expand the brackets, collect like terms, and convert it into standard form does not provide much use. Okay, so that's why we don't really care about changing our vertex form to our standard form. Let's look at it from the other direction, though. What I want to do now is I want to examine going from our standard form to our vertex form. Again, notice that in standard form, all I can see is my shape and my y-intercept. But the most important point on my parabola, that change of direction, my vertex, I can't locate it in there. And I need to know that point. So now we're going to begin the process of changing from standard to vertex. I'm going to tell you that this is going to get a little ugly as we go. I'm going to ask you to hang tight. I'm also going to tell you I'm never going to expect you to duplicate this on an evaluation. So I don't want your focus to be, how can I remember how to do this? I want you to kind of sit back, take in the process. We're going to do a little hopping around, but I think we should be good. Just be patient with it. Okay, for me to go from standard to vertex, I have to be able to get that converted to that. And what that means is I have to somehow get a perfect square in there. So I need to somehow change that standard form and put in a perfect square. So what the process that we're going to follow is actually called completing the square. It's a process that some of you may have some experience with, most of you will not. We're going to walk through that process in a very generic way. Notice, that is as generic of a function as we can have. A, B, and C just represent any number. But we're also going to hop out every once in a while and deal with some specific values so we can see some patterning. Okay, for me to do that, the first thing I notice is I need to factor out that A. So I'm going to take that A and I'm going to factor it out of all terms that contain the variable. Now, you could factor it out from the C as well. I just wouldn't. It's going to require a little extra work later. We want to factor it from all terms containing the variable. Okay, now that we've done that, we can do a quick check and just make sure that if you did re-expand it, there's your ax squared, my a's would divide out, and I'd get back to my bx. Okay, we're good. Now what I need to do is I need to somehow get my perfect square. Well, I know when I expand that x minus h squared, I'm going to get 3 terms. I know that a perfect square as a binomial base has to be a trinomial when it's expanded. That means what I have inside the brackets is missing something. Notice I have the x squared part of it, and I have the single x term part of it. What I am missing is the constant. I am missing whatever the number portion should be. So what I need to do is try to figure out how to put that in there. So what I'm going to do then, oops, I want that in gold. I'm going to copy out what I have, and I'm just going to leave some space. Now, I left a lot of space because I'm not quite sure what I'm going to put in there, but I need to get my constant. For us to figure out what that constant is, we're going to hop out and we're going to do a little bit of patterning. So if I was to ask you, I have x squared plus 4x blank. And I said, okay, if that was a perfect square trinomial, and so there's something that's missing in the blank, what would have to go in there where we could factor it into something like that? Then we could kind of look at that for a second, and I want you to look at that for a second. And maybe we can see that, well, if that was going to factor, I would need to be able to pop in there a positive 4. Okay, why? Well, notice that if we did factor that trinomial now, I would have my plus 2. And if we were to expand that, we would now have our x squared plus 4x plus 4. Yep, we match up. Okay, we're going to try another one. What if I said I've got my x squared and 10x? Okay, you need to try to figure out what should you put in that blank that would allow us to factor that into a perfect square. Take a moment, try to consider it. If we've got it, then hopefully we match up and we say a 25. Because we know that what we would need to have inside the bracket would be a plus 5. Now, I just want you to notice that what my process is maybe isn't that clear in the red case. I could have come up with 2 different justifications for how to get that positive 4 in the end. However, I think my patterning should have been confirmed by the blue case. We're going to try one more, see if we could match up. X squared minus 6x. What should go at the end to make it a perfect square trinomial? Hopefully we came to a positive 9. Okay, let's look at our patterning to see why. If we look at the blue, the one where it's pretty obvious, I know that this middle term of 10 comes together of 2 of the same term. So if I was to break that 10 apart equally, I'm going to break it into 5 and 5. That's what determines the number inside my bracket. Well, how do I get the constant at the end? I know when I expand my bracket, I need to square it. Okay, so we could get a little confirmation then that if I was to factor the gold, it would factor. So what that says is take half of your value, square it. And we can confirm that with the red now. Take half of your value, square it. So I'm going to get rid of all of that patterning. You can obviously rewind it if you want to get any part of that down. And what we need to do now is we need to figure out what value we're going to plug in there. So what do I need to do? I need to take half of that value. So I need half of b over a. Okay, well then that's going to reduce to b over 2a. And now what I need to do is square it. And that's what's going to determine the value that should be at the end as my constant. So if I square the top and I square the bottom, I'm coming in on b squared over 4a squared. Nice. That's the value I need to sub in. Okay, same thing as previous. If you need it, rewind the video. Otherwise, I'm getting rid of that as we go. All I'm going to do is I'm just going to write it over off to the side. We took half and we squared it. So that's what gave us, and I'm going to put this in red, my b squared over 4a squared. Now, I just want you to notice that by me adding that value in, I clearly changed the value of the function. And I should have a bunch of people who are almost like screaming at the video going like, but wait a sec, you can't do that. By me just adding in that value there, I just affected the function. And I'm going to say 100% I did. And I can't just do what I did in red. However, and this is where you almost might view like I'm fudging our work. I'm not. What if I just subtracted that exact same amount out again? Now is my function okay? I want us to notice when we take a peek at that, what I just substituted in has a value of 0. I added in something and I subtracted it right out. So since it has a value of 0, that means I didn't change the value of the gold. Gold is still correct. The gold matches up with the blue. Now you might ask, well, what was the whole point? I'm going to get rid of that 0 I just put down, and I'm going to underline that trinomial. Because if you recall, what we were missing was a trinomial that could factor into a perfect square. Okay. What I've underlined in blue, that's the trinomial I wanted. As ugly as it is, that's the one I wanted. My problem right now is I've got that green fraction on at the end. I've got to get rid of that green fraction. Well, where is the green fraction? It's inside my brackets. And how do I get rid of something from inside of brackets? I expand. So what I'm going to do now is I'm going to expand just the green fraction out of the brackets. Okay, what does that look like then? And I'm going to put this next line in red. I still have the a out in front that I have to multiply in to everything else inside the brackets. But I did multiply the a times the green fraction, and that's what gets me to this. Now, I want you to notice I didn't copy out the green fraction. Notice my denominator is different. What I just calculated was a times negative b squared over 4a squared. And we should be good that I could divide out a common factor of a. So all I did when I wrote down that red fraction of negative b squared over 4a was I just reduced my fraction right away. Okay, we come in on that point and we're doing pretty well. Look what I have on the inside of my brackets. It's everything I wanted. That is a perfect square. So my job then is just factor it. Okay, that means that I'm going to have that factored as a perfect square. Now, if you just look at that and you try to go like, Okay, so now I have to try to think of two numbers that multiply to give b squared over 4a squared and add to get... Let's stop for a second. Remember, you chose the constant because you knew it made it a perfect square. So I'm going to hop off to the right for a second. I'm just going to put up that last example we did. I asked you to fill in the blank to make that a perfect square, and we should have been good to say it has to be 9. Why? Because for you to get the factor, you had to take half of the coefficient on your x. That's what becomes the constant inside your brackets. So if I delete that green, can you see that in that red fraction, what I have on the right? I already did that. I took half of my coefficient. Now, you can also see that here. There is the coefficient on the x. So for me, I need to take half of it. And notice that we match up with the b over 2a. Okay, I've got so many things circled here. I'm just going to get rid of some of that stuff that's circled. So I'm going to get rid of all of this stuff now on the right. And we should be good to then be able to factor there. Okay, the only thing left for me to do is now take this end, and I just made a mistake there. It's got the minus in there. Take that end and collect it all into one term. So we see we have a fraction and a whole value, so we're going to have to get a common denominator. But I also want you to zero in on the negative. Remember, common form is going to say, if you have a choice, like, put the positive term first. So when I go through and I deal with this, I'm going to get my common denominator, and I'm going to write it in a good form. So off on the side, I need to take my c subtract b squared over 4a and put them all together. So my common denominator would be a 4a. That means that I need to multiply my c by 4a. Now I didn't have to change the second one. There is my constant. So on the end, fully simplified, 4ac minus b squared all over 4a. And there we go. Now, I know that it doesn't look it, and I know that it's hideous to us, but I need you to see that what we just have in blue is the same thing as what we have in green. That's our vertex form. Notice what you have in blue is y equals a times a perfect square plus a number. Just almost everything in there is uglier than what you see in green, but they are the exact same thing. Okay, now, was this just like the last one where really what was the point? Was it even useful? It is absolutely useful to us. Okay, why? Well, remember up in the green that our vertex is HK. We can read it there. It's the opposite sign of what we have on the inside and our vertical shift. So if I did the same thing with the blue, and I'm just going to shrink this down now, just to have a little more room to write, that what we end up stating then is, I know that I have a vertex of negative b over 2a and this big ugly y coordinate. I'm going to just tell you, I don't even think it's worth your time trying to remember that. The focus for us should be, look at what your x coordinate of your vertex is. That's pretty straightforward. It's negative b over 2a. Now, I'm hoping that most people coming out of grade 10, you learn that, and maybe we just need a little reminder, or maybe you were never shown why it was the case. You were just kind of told that's what it was, and you were asked to trust it. We can now see why your vertex has an x-coordinate of negative b over 2a. That is so useful for us because now, if I'm given my function in standard form, I can do a pretty quick calculation to get the x-coordinate of my vertex. And since my x-coordinate is my most important point, my vertex is my most important point, I need to be able to find that pretty quickly. Okay, as I said, I hope you didn't get lost in all the hoopla. It does become a pretty ugly process as we go. But I'm hoping that we can now see justification for why we're going to use what we use. So what I want to do now is I actually want to jump in and get used to us taking a standard form and converting it into vertex form. Okay, so let's jump in and play around with a few examples. Okay, you take a look on the screen and you see the instruction. All we're going to do today is convert to vertex form. So what I'm going to do is I'm going to go through an approach that I'm not going to ask you to use. So I would actually just like you to sit back and watch a little bit. I'm going to go through the process of completing the square on this function. So basically what I'm going to do is I'm going to do what we just did in theory in the last one, the process on that most generic quadratic function, and I'm going to tackle it with this specific one. This would be what it would look like. Okay, so I would factor out a 2 from both terms containing the variable. I would then ask myself, what constant do I have to sub into the end of that bracket that would make that a perfect square trinomial? So I have to take half of 8, which is 4, then square it. So what I want to do then is I want to add in a 16. But I know that I can't just add in a 16, so I'm going to subtract my 16 as well. Now I need to expand out that's negative 16 because I don't want that to be part of my trinomial. When I expand it out, I got to multiply it by my a value, my 2. And now I can spend a line factoring and collecting on the end. So I get to that point, and I could now say, there is my vertex form. I can read my vertex from it. I can see my shape. That's what completing the square looks like with a very specific function. My recommendation to you, though, is I think we have a better way. It's not that completing the square is a bad way. I use completing the square sometimes. But I think that we might have a more efficient way given what we just proved. So I'm going to erase all of that. I want you to look back on it in a moment, but I'm going to erase all of that. Because what we just proved is that for any standard form equation, the x value at my vertex is negative b over 2a. So why don't I just use that? Since we've proven it, let's use it. Now, I'm going to ask you to write a line in every time. I think this line is very, very important, especially for those people who are intending on taking advanced functions in calculus. That really what we end up doing is we're going to find, so 4, and I'm actually going to ask you to write in something as well that's based on our shape. We can see that we have a parabola that's been vertically stretched by a factor of 2. So we should know that we have a parabola that opens up. And since it opens up, we know that its vertex represents a minimum. There's a bottom to that parabola. There is no top. So what I want in your statement is for the minimum, which is the vertex, then my x equals negative b over 2a. Now, we're going to amend that statement a little bit as we go. But I think that that is a great statement to start with for the first one, and I'd like you to get that into your notes. So all I want to do then is now use that property. So then why don't I just go and say, well, then x has to equal the negative of my b value, so switch the sign on my b value, over 2 times my a value. Well, for most of you, you're not even going to blindly write down 2 times 2. You're just going to calculate it. X equals 4. What that tells you then is you know that your vertex is 4 something. Well, if you know the x-coordinate of your vertex, then can't you very quickly find the y-coordinate? So what we can now do is we can sub x equals 4 back in. And let's calculate. So I'm going to get 2 times 4 squared minus 16 times 4. And you're just calculating that as fast as you can. Clean it up. 32 minus 64 is a negative 32. Add on negative 7. And therefore, we now know that we have a vertex at 4, negative 7. I want you to notice that the only part that's missing from our vertex form is the easiest part that we can see. Look what's circled up in your original function. Our shape. So the only thing that we need to add in, the same a value. There you go. So as we walk through that process, I want you to just take a quick peek back at that completing the square approach. So like rewind it to that point, take a quick peek and notice that what we're actually working through here is much simpler. Now that you're back, we take a look. Calculating negative b over 2a is pretty straightforward, and subbing in an x value is just a matter of calculating. So my recommendation to you is let's just use that my x-coordinate of my vertex is negative b over 2a to get there, to make that conversion. Now, I'm going to jump back into a little bit of theory because I want us to have at our disposal a little bit of a check. That is, we should be able to kind of work our way through this process and recognize when we've made a mistake or not. It means we're going to have to talk a little bit of theory, but I think that this is going to be useful for us. I'm going to hop back to that first screen that we started off the day with, but notice I've just kind of added in like a new vertex form in a way. Like it's clearly the same thing as the green, but I just wanted to incorporate our negative b over 2a aspect. I'm going to put down some stuff and it's going to get a little ugly, but I just want you to be patient with it again. I think the result is going to help us. Let's say that I take a look at that and I know that my vertex then has to have an x-coordinate of negative b over 2a. So I'm going to sub negative b over 2a into my standard form to find the y-coordinate. So I'm going to replace my x squared with negative b over 2a, and I'm going to replace my x with negative b over 2a. Now, it's not that I don't care about the plus c. Clearly, you need to incorporate that to find the y-coordinate. But what we're going to use is a check. We're not even going to concern ourselves with the c. I want to focus in on just what happens when we sub into the x squared term and the x term. What I'm going to do is I'm going to simplify what we have right now. So I would now have my a, square that, and multiply in my b. Okay, I also notice now that one of my a's will divide out as a common factor. And so this first term becomes a b squared over 4a. My next term becomes a b squared over 2a. And I'm going to stop there because I think that gives us everything on our check. Okay, the first thing I want you to notice. your terms are opposite signs. So if I go and I sub in what I should correctly sub in, my first term and my second term are going to be different signs. There's one thing that I can check. The second thing deals with the actual value. Notice that both of those fractions I have are almost the same. The second one I divide by a 2, the first one I divide by a 4. So notice in that first one, I'm dividing by an extra 2. Okay, what does that mean? Well, then that means that my first fraction, my first value, has to be half of the second terms. Or if you want to think about it the other way, my second term has to be double the first. So when I go through and I sub in, if I've subbed in the correct negative b over 2a value, then I should have a little check between my first two terms. Are they different signs? And is the second term double the first? Or is the first half the second? Okay, let's work our way through and see just a little confirmation with that. So if we look back at our solution to 1a, when we went through and we started to sub in that x value of 4, what confirmation did we have that the x value of 4 was correct? Look at your first two terms once they're simplified. Notice they're opposite signs, and my first term is half my second, or my second term is double my first. That's what tells me, yep, I've got the correct value. I feel really confident moving forward. Okay, keep that one in the back of your pocket so that as you're working your way through and doing some calculations, silly little human error calculations don't trip you up. Okay, what I want to do is I want to spend the rest of the day for us going through and just converting to vertex form. Okay, here we go. Take a look at what we have on the screen now. You've got two problems. All we're going to do for the rest of the day is I'm going to throw maybe some extra quirks at you. Some things where maybe the numbers get in the way, or just some stuff where some things can get a little uglier, just to make sure that we've got the full process. So what I'd like us to do is to walk through B together, because I want us to see how we can really kind of simplify this a little bit. Okay, we have to change it to vertex form. So I know that I'm going to use my x value equal to negative b over 2a. If I know that my x coordinate is negative b over 2a, then that is a formula that we have proved. You don't have to write it down. So rather than writing it there, what I'm just going to say is 4, and then my eyes go, what is my shape? Well, that's a parabola that's opening up. That means that I have a minimum. For my minimum, then what I'm going to write then is x equals, and I'm going to find the x coordinate now. I'm not going to just blindly write down negative b over 2a. So x equals negative 5 over 2 times 1. See, I don't even have to copy down that formula. We're good. Okay, now that I have that, then what I'm going to do is sub x equals negative 5 halves back into my function. And that's going to give me my y value. Now, my recommendation to you is if I have a fraction that I'm subbing in, try to simplify each term, or at the very least each power. So when I sub in my negative 5 halves and square it, I'm going to get my 25 fourths. When I sub in my negative 5 halves times my 2, I might be able to just jump straight to, well, 5 times negative 5 halves is a negative 25 halves. And then my minus 8. Okay, I take a peek at that and I'm going to use my little check. My first term, second term, opposite signs, perfect. My first term has an extra divide by 2 on the bottom than my second term, so yes, it is half of it. I know I'm good. Now all I have to do is finish it off. So my next line then is going to be common denominator on every term. I don't have to change the first one because it already is in quarters. I have to change the second one, so that becomes in quarters. And now I have to change 8 into quarters. There we go. Now, I do have an alternate way to check my solution. And you notice that once I found my common denominator, I have an easier way maybe to check whether one is half the other or double the other. Now I can really see when I have my 25 and my negative 50 that they are opposite signs and one is double the other. Specifically, the second is double the first. Okay, the only thing I have to do now, put everything together. The other nice part is, since it's double, when I take 25 and I subtract negative 50, I know that gives me negative 25. Like it's almost like I have to do very little math. So there's my negative 25, subtract 32 more. That's going to give me my negative 57. And that's all in fourths. Okay, the only thing left for me to do then, write it in vertex form. And so I have my x plus 5 halves. There's my perfect square. Do not forget about that square. Do you know how many times I see students forget about the square? If you don't put the square in, then it's not a parabola, it's a line. Put on my y coordinate that I just found. And my very last step is ensure that my shape is correct. So I'm looking to make sure I got my shape. And in this case, I had a coefficient of 1, so I was good. That's going to look like a pretty common solution for us. Okay, I think we're done with the review then. It's up to you guys now to just get comfortable with the process. So I want everybody to go start to finish on C. Okay, pause the video now. Okay, we're back. So for us, we're going to look at, I should have a statement that when I look at that negative 3 out in front, that's going to tell me I have a parabola that's opening down, and parabolas that open down do not have bottoms, they have a top. That means I have a max. So for my maximum, I know that x equals, and I can sub in my values, my negative b over 2a. Well, I'm hoping that we did not sub negative 9 over negative 6 in, because that fraction reduces to 3 halves. So what I can then write is I'm going to sub x equals 3 halves back into my function. So I'm going to leave that negative 3 out in front, square my power. Maybe I leave the 9 out in front, sub in my power. That's okay as a first line. Now I can simplify each term. So I get a negative 27 fourths plus a 27 halves minus 12. I have the ability to check there that I'm correct and I feel confident. Or when I get my common denominator, I have a chance to check there and I feel really confident. Change the last into fourths and we're good. Okay, negative 27 plus 54, there's my quick calculation. I know it's got to be positive 27. Take off my 48, and that gets me to negative 21 fourths. I'm going to shrink this down a touch because I feel like I'm running out of room, and I need to do what the problem asked me. Put in my shape and put in my vertex. If we have that, then I think we are doing great. So what I want you to kind of work on is, can we get really efficient with our calculation? And obviously we need to be correct on finding our values. Okay, let's try another. I want you to work your way through D. Okay, let's go start to finish. Pause it now. Okay, we're back. So we take a peek at that, and we should have been good to say, I have a positive value out in front, so I have a minimum, that my x value is going to equal 3 divided by 2 times 0.25. So if we kept it as a decimal, then that's going to be 3 over 0.5, which I'm hoping we got to pretty quickly. There's my 6, right? That's 3 divided by a half, which means I need to multiply. There's our 6. So I'm going to sub x equals 6 back into my original. That gives me my 0.25 times 36 minus 18 plus 2. Now, I don't think it's a bad thing in this instance for anybody who actually preferred to work with a fraction. That once we saw the 0.25, I would almost bet that most people would be more comfortable to deal with the 1/4. Okay, we can simplify everything. I have my means to check. I feel really confident. 9 minus 18 gives me my negative 9. Add on 2. So, only thing left to do, put in your shape, put in your vertex. And hopefully we matched up. Okay, we should be feeling very confident with that process, or at least we should be getting there in terms of confidence. Last one that we're going to play through. You take a look at E, and I'd actually like you to go through and try to build a sketch to it too. So we're going to actually produce a sketch, which is where we go in our next topic. But I just want us to maybe see the full benefits of what this process provides. So how about we just be focused on the very first part? Let's use this as a gauge. Can we go through and convert that into vertex form? Picture this one. This is a test question. Everything's riding on it. Okay, pause the video now. Go ahead. Okay, we're back. So I have a positive value out in front. So I have a minimum on my parabola. And I know that my x value is going to have to equal my opposite sign. So negative 3. Right? So switch the sign on 3 all over 2a. So I got to sub in a fraction. I am now subbing in my x value of 3/4. And that's going to give me, square my 3/4. Okay, now I am hoping that we didn't just do this. Because that's going to force us to have to get common denominators of 16ths, which there's nothing incorrect about that. But we could have got away with dealing with a smaller common denominator. Okay, we take a peek. Look at my first term. One of the reasons why I kind of like to leave that 2 out in front is I do have the option for a quick check. And I noticed that when I reduce that first term, it's going to reduce to 9/8. And if I just show that reduction as I've done in red, then I could probably just jump straight to my common denominator of 8ths right away. So now that means I don't have to change the first, but my second fraction will be a negative 9/4. So I'm going to have to double that to change it into 8ths, so a negative 18/8. And now change my 10 on the end into 8ths. There's my negative 80. So just something to keep in mind that I think you could show me that and you're good. That now gives us a negative 89/8, and there we go. So the question itself asked us to write that into vertex form, put on my shape, put in my vertex, and we are good. I have now asked you to go ahead and produce a sketch to that. So what we're going to do is we're going to put down a quick set of axes. And as I said, this is the approach that we're going to address tomorrow. So I wouldn't be overly concerned if we would struggle to produce this sketch today. We're going to talk about this formal process then. But we should be good to be able to kind of at least work through the meat of it, most of it. Okay, we found that we have a vertex at 3/4 negative 89/8. So what I'm going to do is I'm going to put on that most important point, that vertex. Again, 3/4 negative 89/8. So I'm going to imagine that I'm going to go over a little bit. 3/4. and I have to go down a bunch. Now, because I'm on different scales, I don't care about my axes. So maybe I end up saying, that's where my vertex is. I take a look, my parabola is opening up, so I will be able to sketch my parabola on my set of axes. I like that. So I'm going to get rid of all those arrows, and I'm just going to put on my vertex. My parabola is opening up, so I'm going to label my vertex below. Okay, there is the most important point. My parabola opens up. Now I need 2 more points on there. If you recall from first unit, I need 2 more points. Well, this is the nice part. Yes, I could go ahead and sub in an x value and find a point, and I could reflect it across to find another point, or I could deal with transformations and think about a vertical stretch by a factor of 2, shifted to the right 3/4, down negative or down 89/8. Yikes. Or can I get your eyes to just go back to your original equation? We know that that's the y-intercept. That's the nice part about standard form. So that I know then, there's my y-intercept. Now, I do want to do a little confirmation that that y-intercept would be relatively there. I do a quick check. Well, negative 89/8 is like negative 10 and 9/8. So I am a little bit below that negative 10. So yeah, that matches up. So now that I have that point there, I can reflect it across the axis of symmetry to the other point. That has to have the same y-coordinate because I'm reflecting it directly across. Okay, what's the x-coordinate on that? Well, my vertex is right in the middle. So if that's 3/4 and then that's 3/4, then it has to be 6/4 or 3/2. So I'm going to get rid of all of that red. And I got rid of a little too much. And there we go. Last thing to do, connect them with a smooth curve. And you do your best to draw something symmetrical. And there we go. So as I said, we're going to walk through that sketching process in full detail next time. But hopefully that gives us a little bit of context as to how we could go through that process. Okay, I threw a ton of theory at you today, but all of that theory is designed so that you know why you are doing something. That if we weren't shown it in the past, you've now been shown it. If you were shown it in the past, maybe that just revisiting, that second time to see it, we had a little bit of a better grasp. We've also now examined in pretty good detail how we can use that check to get there. Okay, same thing as normal. Job, jump in and get some practice. Okay, good luck.